Hello and welcome to this Revision Monkey video on what's going to be in the 2022 exams. This video is for the AQA specification and it's for Combined Science, and that's the trilogy version of Combined Science, which means that you take 6 exams at the end of your course, all of which are 1 hour and 15 minutes long. And this video covers the major topics of focus for Chemistry Paper 2, and it's for Foundation Tier. First of all, let's look at what's not assessed in this paper. And there's just one topic they've told us won't be assessed, and that is carbon dioxide and methane as greenhouse gases. They have told us the required practicals to focus on, and those are rate of reaction and paper chromatography. And do look out in the description for a link to a video that focuses just on these 2 required practicals. They've also told us the topics which will be the major focus of the exam, and these are rate of reaction, reversible reactions and dynamic equilibrium, carbon compounds as fuels and feedstock, purity formulations and chromatography, the composition and evolution of the Earth's atmosphere, common atmospheric pollutants and their sources, and using the Earth's resources and obtaining potable water. So these topics we'll focus on for the rest of this video, and also look out in the description for a link to some practice questions based on these major foci. Let's start with our initial ideas then of what actually has to happen for a reaction to occur. And this is all to do with collision theories. This is the idea that particles are constantly colliding with each other. But that doesn't necessarily mean that they are going to react. The only way in which they can react is if they have the minimum amount of energy needed for a reaction to happen. And we call this the activation energy. So only if those particles collide with the activation energy or enough energy will they actually be able to react. And when they do so, we can write it as an equation where you'd have reactants on one side and products on the other. And we can calculate the rate of reaction and measure how quickly a reaction is happening. There are a number of different factors that could affect the rate of reaction. They include things such as concentration, which would be really important when you're reacting things with chemicals such as acids. Pressure would be important for reactions involving gases. Surface area would be really important for reactions involving solids. So for example, if you started with a large piece of calcium carbonate, if you were to break that down into small pieces, you're actually increasing the surface area. The final factor that we'll discuss on this page is temperature. Now, all of these factors, if you increase them, you will increase the rate of reaction and how quickly a reaction happens. But it's really important in your exam that you talk about collisions. So all of these things will increase the frequency of collisions, that means how often the particles collide, and increase the rate of reaction. I've underlined this because it's really important. You can't just write that there are more collisions. You have to put that you're increasing the frequency. So this word here is really important. So increasing the concentration of an acid, for example, increasing the pressure of a gaseous reaction, or increasing the surface area will increase the frequency of the collisions, which increases the rate of reaction. It's really repetitive, but it's the same kind of idea for all of these 3 concepts. It's also true for temperature. If you increase the temperature, the particles will collide more often, so we say we're increasing the frequency of collisions and increasing the rate of reaction. However, questions on temperature tend to have maybe a few more marks, maybe 3 or 4 marks compared to above, because you can also talk about the particles moving faster, the particles having more energy and therefore more energetic collisions. And by increasing the temperature as discussed before, more particles will therefore have what we discussed, the activation energy, the minimum energy for a reaction to happen. So there's a little bit more detail you can include when writing about temperature. The final thing that we're going to talk about in terms of a factor affecting the rate of reaction is something called a catalyst. Now, at key stage 3, you would have talked about a catalyst speeding up a reaction. Unfortunately, that definition isn't quite good enough for GCSE, and they actually want you to talk about this definition here. A catalyst is something you put into a reaction to increase the rate of reaction, and the way it does that is it provides an alternative pathway with a lower activation energy. So it provides a pathway with a lower activation energy, so the particles will need less energy to react together. These aren't things that are included in the reaction. They wouldn't be in a word equation or anything like that. They are just something extra that is put in the reaction chamber to help the rate of reaction increase. We're now going to talk about how you measure the rate of reaction. Rate is something that's always measured over time, and there are two ways that you can look at it. You could either look at the amount of reactant used over time, or the amount of product made over time, and either of those would give you an idea of the rate of the reaction. There are two required practicals that you need to be aware of. The first one is involving a reaction with a metal, for example magnesium, with an acid. In this practical, you would put your reactants, your metal and your acid, in a conical flask on a balance. You may well see it in the exam as well with some cotton wool in the top. That's just to stop the acid from spitting out during the reaction. But this cotton wool will still let gases through it. And what will happen, from your understanding of metal and acid reactions, is that hydrogen gas will be produced. And you can see that from the little diagram here. You might see bubbles coming off of the metal. And that will be able to then leave the conical flask. So with gases leaving, atoms leaving, there is actually mass being lost out of the top of the flask. If this was a closed system with a bung in, that wouldn't happen. The balance would stay the same, but because the gases can escape, the balance reading will go down. And what you can do, you can record the mass at regular intervals. So every 30 seconds, for example, you would take the reading on the balance and write it down in a table. And then you could use that data to calculate the rate of the reaction. You could then, for example, answer questions such as how does concentration affect the rate of reaction? And then you could change the concentration, for example, using 0.1, 0.5 and 1 molar acids. In the exam, they may ask you about variables. So in this case, this would be your independent variable that you're changing. The rate of reaction, or the mass on the balance every 30 seconds, would be what you're measuring, your dependent variable. And your control variables that you should keep the same would be things like the mass of magnesium that you're using and the volume of acid. When you're writing about variables, never use the word amount. Examiners do not like you using that word, so make sure you're clear that you're talking about the mass of magnesium and the volume of acid. Temperature would also be an important thing to control because that could affect the rate of reaction. And you may well have to write a method for this practical. A second similar practical looking at rates of reaction would involve two chemicals that you would put into your conical flask. One of those would be sodium thiosulfate and the other hydrochloric acid. And when these two react, they produce a solid. And this is an example of a precipitation reaction because that solid is called a precipitate. And what will happen will will be that it causes this solution here to go cloudy. So first of all, when you put the conical flask on your tile with a cross on it, because the reactants are colourless, you'll be able to see the cross through the tile. At the point that you put these two in the conical flask, you can start a timer and then time how long it takes for the cross to disappear, because a solid will form and this will start to go cloudy and you will no longer be able to see your cross. You could then, like before, investigate how the concentration affects the rate of reaction by changing the concentration of either the sodium thiosulfate or the hydrochloric acid. You can show how the rate of reaction in an experiment changes by plotting data onto a graph. This graph, for example, shows how the volume of gas changes over time. So you could have a setup whereby you have a conical flask with the reactants in it, and you could connect that to a bung, a delivery tube, and a gas syringe. And as the reaction produces gas, you could then record how much gas has been produced by using the gas syringe. When you plot your data, often it will be a curved line of best fit that you're drawing, and you might see questions in the exam such as what is the mean rate of reaction, or what is the mean rate of reaction between two specific time points. First of all, for the mean rate of reaction, you need to be aware of this point on the graph here when the graph flattens out. At this point, as you can see, no more gas is being produced, so that means the reaction has stopped. Therefore, to calculate just the overall mean rate of reaction, you can draw a line up to that point on your graph. If I do it with a highlighter to show you, draw a line up to that point and across, and you can use the data then to calculate your mean rate of reaction. So what you would do is you would take your values along your x-axis here and your y-axis here. On your x-axis you can see the value is 14 because it goes from 0 to 14, and on the y-axis it goes from 0 to 32.5. So to calculate the mean rate of reaction, it would be 32.5 centimetres cubed divided by 14 seconds, and that would give us a rate of reaction of 2.4 centimetres cubed per second. If we take two different time points, the mean rate of reaction here between 4 and 12 seconds, well, for 4 seconds we'd go up to the line at 4 and across, and for 12 up to the line at 12 and across where we've gone already. And then we have to calculate the values in between those two lines we've drawn. So here we go from 4 to 12, so that's 8. And within that 8 seconds we have produced this amount of gas, which is 32.5 minus 20, which is our 12.5. So to calculate our rate, we do the amount of gas we'd produced, 12.5 centimetres cubed, divided by the time it took, which is 8 seconds, and that will give us a mean rate of reaction of 1.6 centimetres cubed per second. If you are doing higher tier, you may also have to do rate of reaction calculations in other units, for example, moles per second. So you won't see that on foundation, but you might see those kind of units on a higher tier paper. The other thing you might have to do with graphs like this is draw lines on the graph to show a higher or lower rate of reaction. So for a higher rate of reaction, that would be one where you had a steeper gradient because more gas is being produced more quickly, and then it must finish at the same point as the first graph because you're not producing any more gas, you're just producing it quickly. So you'll get 2 marks, 1 mark for drawing it the right side of the line and 1 mark for making sure it levels out at the same place. If you were to draw a lower rate of reaction, that would be below the initial line because less gas is being produced in the time, and again it must finish off at the same place as before. Moving on then, we're going to talk about reversible reactions now, and you should be thinking to yourself whether you know the symbol for reversible reactions. The symbol is 2 half arrows going in opposite directions from each other. This here is an example of a reversible reaction that you need to know about. In this reaction, we start off with hydrated copper sulfate. Hydrated means with water, so this is blue, it's with water, and this turns into anhydrous copper sulfate and the water is released. And this over here, I can't write in white, but this is a white powder. But because this reaction is reversible, what it means is if you have these 2 products, they can react again to make the hydrated copper sulfate. So one way of the reaction we will call the forward reaction, and the reverse we call the backward reaction. And if we do the reversible reactions in a closed system, so no reactants or products can leave, eventually the reaction will look like it's stopped. So hydrated copper sulfate will break down into these 2 products. These 2 products will then react together to make hydrated copper sulfate, and this will be happening continuously, but it will look like the reaction has stopped. And when this happens, the reaction has reached equilibrium, which means that the forward and backward reactions happen at exactly the same rate. It doesn't mean there's the same amount either side. There could be different concentrations of the reactants or products, but it just means that the forward and backward reactions are happening at exactly the same rate. This reaction here in the forward direction is an example of thermal decomposition. You can identify thermal decomposition reactions sometimes because there's nothing else reacting on this side. This itself is just breaking down or decomposing under heat. So if you heat this up, it will break down into these 2 products, and that is an example of thermal decomposition. In the forward reaction, therefore, it takes in heat, so it is an endothermic reaction, whereas the backward reaction is exothermic. And that's always true for a reversible reaction. If it's endothermic in one direction, it is exothermic in the other direction. Now we're going to move on to the next topic, which is all about organic chemistry, which is really talking about molecules that have carbon in them, or carbon-based molecules. First of all, we'll look at hydrocarbons, which contain 2 elements, hydrogen and carbon, hence the name, hydrocarbons. And we'll look at the process of fractional distillation and the process that follows that, which is cracking. First of all then, our hydrocarbons. There's 4 that we need to know about in detail, and to remember those, a little rhyme that goes monkeys eat peanut butter. And if you remember monkeys eat peanut butter, you will remember the first 4 names of the hydrocarbons. These are methane, ethane, propane, and butane, which I'll draw for you in just a minute. The reason that they are in this order is that because they go up in order of the number of carbons they have. You can see methane has 1 carbon, ethane 2, propane 3. All around those, it is a saturated molecule, so that means it is full up of hydrogens, nothing else can bond to it. All 4 bonds for each carbon are taken. These are covalent bonds, and they are single covalent bonds because there's just 1 line. We can write the formula for methane because it's got 1 carbon and 4 hydrogens, it's CH4. Ethane has 2 carbons and 6 hydrogens. Propane has 3 carbons and 8 hydrogens. The general formula for these molecules is CnH2n plus 2. All that means is for whatever number here that you have, to work out the number of hydrogens, you double it and add 2. For example, here, if you double 2, add 2, you can work out that it has 6 hydrogens. All these molecules are examples of alkanes, and because they are very, very similar in structure, they are said to be all part of one homologous series of chemicals. Okay, they have a very similar structure, they're only slightly different because they've got different number of carbons to each other. With all that information then we can draw butane, because that's our next one in the list, and we know it therefore has 4 carbons, and if we use this formula we know that it's got double the number of carbons, add 2. So if you double 4, add 2, that works out as having 10 hydrogens. And we can then draw that with our carbons here with single bonds, and then around that, fully saturated, we would have hydrogens. Make sure that all of these are drawn in capitals, because whenever you write elements, you write them as capital letters. All of these alkanes then, you may have to draw, you may have to write their formulas, and you also need to know that they are useful fuels. That brings us on to the next part where we talk about combustion. Combustion is when we take these alkanes or any other fuels and you react a fuel with oxygen. So for example, when you're heating a fuel, it is reacting with the oxygen that is found in the air. And when you do that, you get these products. You get carbon dioxide and water. And these products are exactly the same whatever alkane you use. So if you have any of these reactions, always the products will be carbon dioxide and water. Propane plus oxygen would make carbon dioxide plus water. Butane plus oxygen would also make carbon dioxide plus water. You may well have to write these as chemical symbol equations as well. So we'll take the top one here, methane plus oxygen would make carbon dioxide and water. And finally, you may be asked to balance the equations. So to do that, if you make a list of how many of each element that you've got on each side. On this side we've got just 1 carbon, 4 hydrogens and 2 oxygens, 1 carbon, 3 oxygens and 2 hydrogens. So there's several things we need to balance. Let's start off by trying to balance the hydrogens. You can only ever put numbers in front of the molecules. So if we put a number in front, it will double that and it will double that. So this time we have got 4 hydrogens and 2 oxygens here and now 2 here. So we've got 4. We're still not balanced because of this oxygen, so we need to put a final 2 here, and that will then have our balanced equation. If you're struggling with these, I do have a separate video on balancing equations that you can watch. Next we're going to look at fractional distillation. And with fractional distillation you start off with a mixture of different lengths of hydrocarbons. And this is because in the bottom of the fractional distillation tower we put a substance called crude oil. Crude oil is something that is made over millions of years. It's a finite resource and one day it will run out. Because it takes so long to produce, we are using it faster than it can be produced. It's made under deep pressure under the bottom of the sea, and it is made from the remains of marine organisms that died millions of years ago. Inside that crude oil, which is a thick black sludgy substance, there will be a mixture of different lengths of those hydrocarbons. So we drew them in detail before, but if I just draw them now as little strands, you would have short ones, medium-sized ones, and really long hydrocarbons. So as a mixture, they are not particularly useful. We need to separate them up into different fractions or different lengths. So in the bottom of the fractional distillation tower, there will be a big furnace to heat the crude oil that goes in. The reason that they separate is because these fractions here have different boiling points. So the short molecules here have low boiling points, and they evaporate straight away and start to rise up the tower. And they will actually come out the top of the tower. Here, the smallest ones come out as refinery gases, and then the slightly longer ones, longer again, until at the bottom you get the really long fractions coming out. So we need to know that the short chains come out the top, the long chains come out the bottom. The short ones have the low boiling points, and the long ones have the high boiling points. The key words that you need to use to describe how the process works are evaporation, the idea that these short chains first evaporate. When they rise up the tower, they will cool down and they will condense into a liquid. And when they do that, they will run off at different points in the tower. So the short ones come at the top, and then the slightly longer ones will reach their boiling point. They will evaporate. They will rise up the chamber, cool and condense, and so on and so on. At the bottom, you get really long chains that are useful for things like bitumen. Bitumen comes out the bottom of the tower. It can be used on roads. It's a really thick, gloopy substance. We call that a viscous substance when it is thick and gloopy. So the molecules that come out of the bottom are more viscous, whereas the ones at the top of the tower, they flow easily. A couple of other keywords that you need to write about. The ones at the top of the tower are more flammable and more volatile. Volatile means they turn into a gas easily. Different fractions come off then. All of them are useful fuels, or most of them are useful fuels, and they can be burnt in heated and react with oxygen in a combustion reaction to release energy. For example, somewhere on the fractional distillation tower you have fractions that are used in petrol, and slightly lower down you'll have fractions that are used in diesel. Why I've highlighted these two is because this will come really important later on when we talk about cracking. So whilst most of these products are used as fuels, like we said, they're also described as a feedstock for other chemicals. That means they are the starter products for making other important things such as polymers, which are plastics, and lubricants. On to the process of cracking then. This follows the fractional distillation process, and it's where you have long chain hydrocarbons that you then heat up and crack to make shorter chains, and the product of this will produce an alkane again, like we talked about before with these single bonds, and it will also produce something called an alkene, which is a different homologous series. For example, this could be cracked absolutely anywhere, but for argument's sake I'm going to crack it here, and I'm going to make this our alkane and this our alkene. If we're to draw the alkane then, it's one with 3 carbons. So we would end up with a 3-carbon alkane, complete with hydrocarbons all the way round like the alkanes. And we will remember that this one from before, it's got 3 carbons, so monkeys eat peanut butter. We'll call it propane because it's got 3. And the second product is an alkene. This is slightly different. Whereas we said this was saturated, alkenes are unsaturated, which means it still has its 5 carbons from this cracking process over here, but one of the pairs of carbons has a double covalent bond. So when we go to complete this with carbons, when we go to complete this hydrogens, because carbon can only make 4 bonds, it's already made 2 here, so we can only add 2 more on. If we look at this carbon, it's already made 1, 2, 3 bonds, so we can only add 1 more on. And I could have added that here or above, it doesn't matter. This one can have 2 more hydrogens, 2 more here, and 3 more at the end. And this is our alkene. So the cracking process makes these really useful alkenes, and why these are important is these are the ones that go on to make plastics that we call polymers. So polymers are examples of plastics. So it's quite fascinating really that from that crude oil that was made millions of years ago from crushed organisms that were floating around in the sea, we can now make our everyday plastics that we find really useful for a number of different appliances. Now there's one way that we can test for these alkenes, these unsaturated molecules. Because these are more reactive, we can use a test with bromine water. If we add bromine water to an alkene, it will go from orange to colourless. You can never ever write clear in the exam, you must write colourless because there's no colour at all. So it goes from orange to colourless. Whereas if you added it to an alkane, that would just stay orange. That's our way of telling whether we've got an alkene or not. Now this cracking process can happen under a number of conditions. It can happen as steam cracking or catalytic cracking. In steam cracking, the long chains are mixed with steam and heated. And with catalytic cracking, they are heated over a catalyst. One way that cracking, for example, can be useful is linked to the 2 products we talked about before, which were diesel and petrol. Diesel, we said, was a longer chain hydrocarbon, so we could potentially crack diesel to make petrol and other products as well. And why we might need to do this? Well, for example, if the demand of diesel cars went right down and the demand for petrol cars and petrol as a fuel increased, you might suddenly need to turn a lot of your diesel into petrol to meet that demand. So regularly in the exam they'll talk about the supply that's available against the demand from the consumer and ways to get around it. First of all, something that only contains one element or compound is called a pure substance. So for example, you could have a pure substance sample of oxygen, maybe a jar containing only oxygen molecules and nothing else. That would be determined as pure. If you had anything else in there, like any water or any carbon dioxide, you can no longer call that pure. You can have a pure sample of a compound, for example, sodium chloride. As long as that sample only contained sodium chloride, you can call it pure. The other key word for this topic is formulation, and that is a useful mixture made from a recipe for a specific purpose. So it can't be any old mixture, it can't be air, for example, which is any mixture of gases that we have around us. It has to be one that we have man-made and purposefully made to do a particular job. So it's got the word formula in it, so that will remind you it's following a particular recipe, a particular formula to make a desired product. For example, things such as paint we would describe as a formulation. Lots of other products as well, like food products. We put lots of different chemicals and lots of different foods into sources, and that would be a very specific formulation. Paint, for example, will include a number of different things in very particular amounts, such as the pigment, which will give it the colour, the solvent, whether that be water or an oil-based solvent, a binder to bring everything together, and different additives as well. So all of these would be mixed together in very specific amounts following a recipe to make a paint with a very particular purpose. The way we can recognise a pure substance is by their melting and boiling points, because we have standard tables available to us which show us the exact boiling point and melting point of pure substances. If they were not pure, you would not be able to melt the substance at this specific temperature. For example, if you were testing a sample of copper and you came out with a melting point of 1080 degrees C, that is not pure because it is very slightly different to 1083, which is the correct melting point for copper. So this could mean that it has some impurities in it, such as maybe a bit of sulfur or another element in there which is affecting the melting point. So you need to be able to understand these tables and understand data on melting and boiling points to determine the most pure substance. Next, we're going to look at chromatography, which is an important required practical. It's important because there's not many required practicals in this second paper for chemistry, so it's one that I suggest that you really get your heads around. The reason you do chromatography is because you want to separate a particular substance, for example, a dye or an ink. It's most often coloured substances that are separated in chromatography. For example, this can be used in the food industry to investigate if there are particular banned food colourings in sweets, for example. If we follow that example through, we would perhaps put on our chromatography paper a sample for our banned food colouring. And then we would put our food colouring that we would find in our particular sweets, perhaps two different samples, A and B. We would then put these on a pencil line on the chromatography paper. The reason we use a pencil is because if we were to put an ink line on there, the ink would also smudge and move up the paper. We would then dip the chromatography paper in some solvent. That is what dissolves the ink, and that could be water or it could be something like ethanol. And really importantly, you don't want to put the solvent above the line. It has to be below the pencil line that you've drawn. Again, otherwise everything else will smudge. So just a small amount of solvent in the bottom is fine. As the solvent moves up the paper, it will dissolve the dyes, and the particles that are in the dyes will dissolve and move up the paper. At some point, that solvent will stop moving up the paper, and this point is called the solvent front. And this then allows the different colours and the different particles in the substance to be separated out on the paper. And by comparing them, you can see if they contained the banned food colouring. For example, here we've got a match with the yellow here, we've got a match with the green here, and we've got a match with the blue here, suggesting therefore that these sweets here may not be fit for human consumption if they contain this banned food colouring. Common thing that they might ask in the exam is why you would want to put a lid on the experiment, and that is to stop the solvent from evaporating. You would then leave your chromatography paper to dry, and the picture that it creates is called a chromatogram. Now in the exam they probably won't print those in colour, so instead you will just see them as dashed lines or dots on your exam. So next we are going to look about how we can use these to do some very important calculations for chromatography. We can use these chromatograms to calculate something called the RF value, and we do that by measuring the distance travelled by the substance divided by the distance travelled by the solvent. Now on your diagrams in the exam they will indicate where the solvent line is, or the solvent front is. So I'm going to draw it on here. So if I wanted to calculate the RF value of this substance, I would calculate the distance that the solvent moved, and I would, from the middle of the sample, calculate the distance that the substance has moved. For example, if this was 5 centimetres and if this was 10 centimetres, I would calculate my RF value by doing 5 centimetres, because that's the distance travelled by the substance, divided by 10 centimetres, because that's the distance travelled by the solvent, and I would get an answer of 0.5. With chromatography there are two different phases. There are the mobile phase and the stationary phase. Within the mobile phase, that's when the substance has dissolved in the solvent and moving up the paper. And in the stationary phase, that is when it's interacting with the paper. So depending on how long the substances spend in the mobile and the stationary phase will determine how far it moves up the paper. So for chromatography, not only we have to write a method to show how to set up a chromatography, you will also have to calculate RF values as well. First of all, we'll talk about how the atmosphere evolved. So Earth is approximately 4.6 billion years ago, we think, and the early atmosphere, we believe, was mostly carbon dioxide. So similar to what the atmospheres of Mars and Venus are like today. Around that time there was a lot of volcanic activity, and these volcanoes were spewing gases into the atmosphere. So we had carbon dioxide going into the atmosphere, but we also had other gases such as methane, CH4, ammonia, NH3, nitrogen as well, and water vapour. That water vapour went on to condense to form the oceans. Later on, after the formation of the oceans, algae, and later on from that, plants evolved. So algae came first and then plants, and they both do a process called photosynthesis, which you should be familiar with from biology. In photosynthesis, they take carbon dioxide, and water to produce glucose and oxygen, and that balances out like so. And in this process, they started reducing the amount of carbon dioxide in the atmosphere because they were taking that in and they were storing it as glucose, and they were then storing that as starch and using that within the growth of the plants, and they were releasing oxygen. So plants and algae played a massive part in reducing the CO2 levels in the atmosphere and increasing the oxygen levels, which then led on to the evolution of animal life and so on and so forth. Carbon dioxide gradually decreased, not only because of photosynthesis and plants, but carbon dioxide also dissolved in the oceans, and there it was locked up in things such as, I'll write it up here, it became locked up in the shells of marine organisms. So marine organisms that had calcium carbonate shells, for example, used that carbon dioxide and it was locked up. It's locked up in sedimentary rock. And it was became locked up eventually, after several millions of years, in fossil fuels because of the fact that it was locked up in those carbonate shells of the marine organisms. So gradually we've gone from a situation where our atmosphere was mostly carbon dioxide, but where it's dissolved in the ocean and got locked up in things such as rocks and shells and taken in by plants for photosynthesis, and gradually the carbon dioxide levels have decreased. So now on our in our atmosphere, carbon dioxide is actually a trace gas. There's only approximately 0.04% of carbon dioxide in our atmosphere. There's approximately 20% in your exam, they'll round that down to 20%. And with nitrogen, which has just creeped off the corner here, we say there's 80% of nitrogen. We normally round that up in the exam. And there's a very, very small percentage of trace gases, things like argon and carbon dioxide in the atmosphere. However, even at 0.04%, this carbon dioxide is causing massive problems because it is causing global warming, which we'll talk about next. Final bit that we'll talk about in this topic is air pollution. There are 4 different things that you need to be aware of. The first 2 come about from incomplete combustion. That's when you burn fuels and there is not enough oxygen. And in those circumstances, you can produce solid particulates, which are essentially bits of solid carbon or soot, or carbon monoxide, which is similar to dioxide, but there's only one oxygen this time, hence it's monoxide. The solid particulates can cause global dimming. So if they're up in the atmosphere, they're reducing the amount of light that can get through the atmosphere and cause a dimming effect. They also have, both of them, respiratory problems associated with them. So if you've got solid particles that you're breathing in, obviously they can get into your lungs and cause all sorts of problems. Carbon monoxide is toxic, so that's a really big problem. It's the silent killer. So if you have a faulty boiler or something like that, and it's undergoing incomplete combustion in there, and you're releasing CO, if carbon monoxide is released, it doesn't smell, you don't notice it's there, but it can silently kill you because it's toxic. What it does is it stops your body getting enough oxygen because it binds to hemoglobin in your red blood cells, and that's what oxygen normally binds to as well. So it stops your body from having enough oxygen. Because if the hemoglobin in the red blood cells has carbon monoxide bound to it instead of oxygen, when you're breathing in you can't get enough oxygen and you will soon die from that. Sulfur dioxide is SO2. This comes about if you have sulfur as an impurity in your fuel and that reacts with oxygen, you end up with sulfur dioxide, and that can cause acid rain. This nitrogen oxides can also cause acid rain, both of which can both lead to respiratory problems as well. Nitrogen oxides are formed at very high temperatures. So they are formed inside the car engines, for example. And they are formed because nitrogen reacts with oxygen, but this only happens in particular conditions at very high temperatures. And when these nitrogen oxides or sulfur dioxides, when they rise into the atmosphere and dissolve into the water in the clouds, that is when they then form acid rain. First of all, a couple of really important keywords. The first one is renewable. That word is given to resources that reform at a similar rate or faster than we use them. That really means if we use them up, we can replace them quickly. However, finite resources are the ones that we need to take real care about because they aren't formed quickly enough to be considered replaceable. So these take so long to make that if we use them up, that's it. They can't be replaced within our lifetime. So the finite resources are things such as fossil fuels. So that includes our coal, oil, and our natural gas. And things such as nuclear fuels. Now, these we rely on really heavily at the moment for electricity production, for heating, for cooking, and all of those things. However, really what we should be looking at is trying to use more renewable resources, so things such as timber and plants. And in terms of electricity production, you'd have renewable resources such as wind and water, etc., because they can reform at a similar rate or faster than we use them. If we grow plants, we can chop them down and use them as a fuel, as a biofuel, and then we can grow some more plants. However, coal, oil, and natural gas take so long to make, they take millions of years. It's impossible to use some coal and then produce coal at the same rate. So we are using up these finite resources very, very quickly, and our drive should be towards trying to reuse more renewable sources in the future. And the whole point we'd have that drive is to develop a sustainable development. And this is development that meets the needs of the present society without damaging future generations. And what that means is, yes, at the moment, if we wanted to, we could use all the finite resources available to us. However, that would have a massive impact on future generations and we would just destroy the planet. The sustainable development is taking that idea of not completely consuming all that we've got now and trying to develop new technologies to make sure that not only our generation the needs of our generation is met, but also those of future generations. Next, we're going to talk about potable water. Potable water, or you may say potable water, is water that is safe to drink. It is not pure water. If we looked at a topic previously where we looked at pure substances only contain one element or compound. For it to be pure, it would only contain the compound H2O. However, potable water is not pure because it does contain some dissolved salts and other substances, but for it to be safe to drink, it must just contain low levels of salts and things like microbes that can make you ill. So it's not completely pure, but it is just safe to drink. So when we're trying to create our potable water for a massive population of people, we need to first of all think about the water source. Now there's two main types of water source. There's surface water, which is the water that is found in things like reservoirs and lakes and rivers. And there is also groundwater, which is found in rocks underground. And it will depend where you are within the country or within a particular part of the world, depending on whether they are accessing surface water or groundwater. But regardless, the first step is always the same in each process. The first thing that you need to do is filter any of the large solids out of the water. So you'd first of all have a wire mesh, and you'd run all your water through the wired mesh, and that would get out the really large solids such as twigs, plastic bags, anything, shopping trolleys, whatever's in your river and in your water, and that will get rid of all those large solids. The next is a slightly finer level of filtration, and that is using gravel and sand. So you would have a layer of gravel, layers of sand, and you would pass all of your water through that. So in the gravel you get maybe smaller bits of leaves and things collecting, and in the sand any really, really small bits of solid that you don't want in your water. So after those two processes, you've got all of the visible things that you can see out of the water, the larger solids and then the smaller solids, and it might well then look like it's safe to drink. However, it's not. It must go through a further sterilisation process to kill the bacteria and other microbes, so like viruses and fungi and things like that are in the water. And there's three ways that you could do that. You could either use chlorine or ozone or UV light, or you might use a combination of those, but all of those will help to sterilise the water and can kill the bacteria that are in there. Within the UK, or certain areas of the UK definitely, there is a final step that people go through, not to make it safe to drink, but just an additional step. So all of these steps here will then lead to safe drinking water that can come through your taps, but some areas also add a chemical called fluoride. You need to be aware that this fluoride is good for your teeth, but it's very controversial because there is no choice. There's some people campaigning in some areas because they're really upset that the companies are pumping fluoride into the water, because they're worried that the fluoride would have certain detrimental side effects that aren't fully studied yet. But most of the companies and the councils say that the benefit for healthy teeth outweighs the potential side effects that have not yet been verified. But a lot of people say because they've got no choice in the matter, it is not fair for companies to be able to be doing this. Okay, so this is all good and well if you are lucky enough to live in a country that has access to sufficient surface water and groundwater. So if it rains a reasonable amount in the year, you're going to have enough water to be able to drink and meet the demand of the population. However, some really hot countries do not have that benefit. In those countries, to produce potable water, which is the water that is safe to drink, instead they might have to go through different desalination processes. And desalination is whereby they are removing the salt from the water. They will still go through the sterilisation processes as well, but for desalination there's two different options. One of those is reverse osmosis, which is a really new technology, and the other one is distillation. Now, distillation forms part of a required practical, so I'll talk about that in detail in the next slide. So if, for example, in this diagram we have seawater on the right and we have water with low levels of dissolved salts on the left, we would want to extract the water from the seawater if we lived in a country where we couldn't have enough surface water. Normally, with osmosis, thinking back to biology, osmosis is the movement of water from a more dilute solution, where there's more water, to a more concentrated solution where there's less water. So normal osmosis in this case would normally see the movement of the water, which is the blue circles, to the right hand side. That would be normal osmosis, because here there are more water particles, here there are fewer, so it would be moving from a dilute to a concentrated solution. However, reverse osmosis is the new technology which will see the movement of water move in the opposite direction. And to do that on this side here, you would require a lot of pressure, and you would have a membrane here which is selective that only allows water through. And in this case, with this pressure applied to this side, you can actually have a case where you reverse the direction of osmosis and the water particles move from a more concentrated solution to a more dilute solution. So in this way, in seawater, you have a lot of salt, but you can still get the water moving out of that salt water into the supply that you want. So this is really a new technology for countries that don't have those access to high levels of surface water or groundwater. Distillation is the second process by which countries can extract water from salt water. This is a required practical that you need to be aware of. With distillation, the basic setup is you have often a round bottom flask with your salt water solution in there. It doesn't have to be salt water. You can separate water from muddy or dirty water or wastewater as well. And you apply heat to that flask. So the main disadvantage of this is that it requires lots of energy and therefore costs a lot to get our potable water. The water within the solution will evaporate when it reaches its boiling point, and it will go up this tube here. This thermometer in the top just helps us determine when the water is boiling, because water boils at 100 degrees C. In this condensing tube, you have cold water running around the tube, not through it, just around, and this makes this part of the tube particularly cool because the water's running around here. And what will that mean is the evaporated water that goes down this side arm then condenses in the tube and turns into a liquid which is collected at the end. Now with distillation, not only is your water potable, but is also pure. Okay, in here, because you are doing the distillation process, only the water particles are evaporating. When they reach their boiling point, you're leaving all of the dissolved salts in the flask and you are getting pure water. The final topic for paper 2 in chemistry is all about how we treat wastewater. We said previously that humans have a massive impact on the environment through their pollution of the land, air and the water, and humans produce a massive amount of wastewater that needs to be treated before it can go back into the water cycle, into the rivers, for example. So wastewater comes from a number of places, such as toilets, bath water, washing up. It also is produced a lot in agriculture. Runoff from the land that ends up in the drainage systems, all the slurry from the farm and things like that. And it will cause water that needs to be treated so that it can go back into the rivers and go back into the cycle. First of all, then, there's a screening process whereby large solids are removed. Little bit like before when we were talking about potable water, you'd have a filter that removes any large twigs or anything that's in the wastewater. You then have a sedimentation process whereby you allow that wastewater to settle in large tanks. And when it settles, you get two things produced. You get the heavier solids fall to the bottom and produce a sediment or a sludge at the bottom. And you get the lighter products at the top, which we call the effluent. So this water will be left in these tanks for quite a long time and allowed to separate, and then two different processes take place depending on whether we're treating the sludge or the effluent. So for the effluent, that undergoes aerobic digestion. So this top bit is removed from the tanks, and then the air is pumped through the effluent. And this encourages bacteria to break down any organic matter. And then this is released back into the rivers. The sludge, however, is treated slightly differently. Again, it's broken down by bacteria, but in anaerobic digestion. So it can go into really large tanks called anaerobic digesters. Some farms have their own to treat this, and this time it's in anaerobic conditions without oxygen. They're broken down by bacteria. But in this process, methane gas is produced. Rather than releasing this into the atmosphere, which is a greenhouse gas, which we wouldn't want, this is then used as a useful fuel, and then the remains are used as fertiliser and put back onto the land.